Hey folks, this is Dr. Sweeney, and what we're going to be looking at today is going to be looking at basic circuit problems utilizing second order differential equations. And so what you're going to notice about these circuit problems, if you've already looked at spring mass systems, is that the differential equations for circuit problems and spring mass systems are very, very similar. And in fact, they utilize almost entirely the same set of solution methods. The math looks pretty much identical, and the only difference really is the interpretation. So when we're interpreting things from circuit problems, we're really looking at like what's happening to the charge over time. And when we look at the spring mass systems, we're talking about the displacement away from like some kind of equilibrium. So in many ways, circuit problems are even easier to understand than the spring mass system problems. And they are, in fact, somewhat easier to do as well. So with that stated, let's kind of get started and take a look at the basics of a circuit and the basics of our variables for the circuit. So we'll start out and we have the current for the circuit. We're going to call that I of t. And then we have Q of t is going to be our charge. And the relationship between the charge and the circuit is going to end up being this issue right here, which is that dq dt or q prime of t is going to equal I of t. So essentially, if we want to find Q of t and we have the current, it's going to be the integral of I of t dt. Then we have resistance, we have inductance, and we have capacitance. And all three of these, they're going to be constants. And they're all going to be greater than 0. So they're constants that are all greater than 0. And that plays a really big role inside of our work too. And then we'll have this idea of the electromagnetic force, which is going to be represented by a function. Oftentimes it's going to be a function of cosine or a cosine function of some sort. And it's going to be like the equivalent of a forced oscillation when we look at the spring mass systems. So here is our circuit, and basically how our circuit is going to work is that we'll close the circuit right here. Here's closing the circuit, and then that allows the charge to run through, or allows the current to run through the circuit. And the capacitance, the resistance, and the inductance, they all represent kind of damping forces on the current or on the charge inside of the circuit. And the EMF, much like the forced oscillations, is going to supply charge. So it supplies charge into the circuit. If we don't have an EMF, and we'll look at this in just a second, what we're going to get is we're going to get a homogeneous differential equation. On the other hand, if we do have an EMF, then our differential equation, our baseline differential equation, is going to be L, our inductance, times Q double prime, plus R, resistance times Q prime, plus 1 over CQ, and that's going to end up equaling F of t, which is our EMF. So here are our basic equations. We've got that LQ double prime plus RQ prime plus 1 over CQ equals F of t. And if we kind of just divide through by L, we're going to get a standard formed second order differential equation with constant coefficients. So we get R over L Q double prime plus R over LQ prime plus 1 over LCQ is going to equal 1 over L F of t. And notice, again, because R, L, and C are all greater than 0, these are positive constants. That's going to play a big role for us. And that's if we have the EMF. Without the EMF, what we get is we get a homogeneous differential equation. And for our purposes, we're going to utilize our methods for solving homogeneous second order differential equations using constant coefficients. We'll have an initial charge, that's Q naught, and then our initial current is I of t, which is I naught, or more likely we call that Q of t, Q prime of t. And Q prime of 0, rather, I should say. And so this here, or these three equations here, or this set of equations here, represent our initial value problem for our circuits. We also have a phase mode form for circuits when what we end up having is we end up having complex solutions to our differential equations, or when we have solutions that are in forms of cosine and sine. So if we have a solution of the form, let's say, for example, we have y of t equals e to the at c1 cosine bt plus c2 sine bt. And c1 and c2 are the constants that we get from utilizing our initial values. What we can do is we can actually make a change of variable in order to change this into what's called the phase mode form. So if we take a right triangle and we imagine that we have phi as this angle, the one that is opposite the vertical side, And we're gonna call A naught, we're gonna equal the square root of C1 squared plus C2 squared. So it's basically the length of the hypotenuse when C2 is the vertical side and C1 is the horizontal. Then phi, utilizing some trig, is gonna end up equaling tan inverse of C2 divided by C1. So consequently, what we'll get is that C1 is gonna end up equaling A naught cosine phi, and C2 ends up equaling A naught sine phi. And this is exactly the same as what we did with spring mass systems. What we'll do is we'll now substitute back into y of t. So we get y of t equals e to the at times a cosine bt, cosine phi, plus a naught sine bt, sine phi. And then we're going to utilize the trig substitution of the trig identity that cosine of b minus phi, or bt minus phi, is actually equal to cosine bt cosine phi plus sine bt sine phi. Essentially our difference of angles. And so when we do that, what we're going to get is we're going to get e to the at times cosine bt minus phi. In this form, it actually allows us to understand the equation a little bit better, or inside of a more traditional form, where we get, oh, pardon me, and this should be an A naught. A naught is our amplitude. So that's the square root of C1 squared plus C2 squared. So that's the amplitude. Phi is our phase shift. And our period ends up being sine, or not sine, excuse me, our period ends up being 2 pi over b. And so that tells us quite a lot about what's happening inside of the system outside of this e to the at term, which we'll talk about a bit more in depth in a little bit. So now we want to talk about something called damping. And damping is important because damping tells us the extent to which the structure of the circuit is going to restrict the free flow of the charge. So essentially it's going to tell us whether or not our charge goes around the circuit once, more than once, or less than once on a single charge. And so whenever we're looking at this, we're going to be looking at it in terms of the homogeneous dE, which for us is no oscillation, no EMF. And so our differential equation is going to be Q double prime plus R over L Q prime plus 1 over LC Q equals 0. Because R and L and C are all constant coefficients, and in fact are positive coefficients, this actually tells us that we can use our constant coefficient method for homogeneous differential equations. So what we're going to do is we're going to get an auxiliary polynomial of r squared plus r over L r plus 1 over LC, and we're going to set that equal to 0. Using the quadratic, we'll end up getting r equals negative r over L plus or minus the square root of r over L squared minus 4 times 1 over LC, all divided by 2 times 1. Doing a little bit of algebra, we end up getting r equals negative r plus or minus the square root of r squared minus 4 over 4L, divided by C, all divided by 2L. For our purposes of damping and telling us about damping, we're going to concentrate in on this r squared minus 4L over C. And the reason why is because it's going to tell us the kind of roots that we're going to get in terms of our solutions to the differential equations. So remember, we've got 3 different kinds of roots that we could have. We could have repeated roots, we could have distinct real roots, or we could have complex roots. And each one has a different set of solutions for the differential equation, and they look very different from the standpoint of damping. So let's take a look at those. We'll start with the concept that we have an overdamped circuit. And we have an overdamped circuit that actually tells me that that discriminant there, r squared minus 4L over C, is going to be greater than 0. So that means that we have 2 distinct real roots. And our solutions are going to end up looking like y of t equals C1e to the RT plus C2e to the R2t. So 2 different r's, right? 2 different real roots. We'll call this R1 and R2. And so consequently, what's going to end up happening is that our charge is basically going to start up here and it's going to decrease towards 0, pretty quickly, because if you remember, A1 or R1 and R2, they're going to end up being negative. Right? R1 and R2 are both negative. On the other hand, if we look at something that's called critically damped, what we're going to get is that R squared minus 4L over C is going to equal 0. And this means that we're going to end up having repeated roots. And when you have repeated roots, you're going to get that y of t equals C1e to the RT plus C2te to the RT. The t multiplier here inside of this solution actually tells us that we're not going to get as extreme a damping, or potentially not as extreme a damping, as we would get in the case of an overdamped situation or scenario where we have both of those functions pushing the charge towards 0. But it still is moving towards 0. So again, we're going to get basically the function is going to increase in charge and then taper off towards 0. Taper off towards the equilibrium of charge of 0. In the case of the underdamped situation, we're going to get that R squared minus 4L over C is less than 0, right? So this is a case in which we get complex roots. And if you remember, when we end up with complex roots, we're going to get y of t equals e to the at, where a is the real part of the complex solution, times c1 cosine bt plus c2 sine bt, which is essentially, or not essentially, is in our phase mode form is going to be a naught cosine bt minus phi. If you look at this here, what we've got is we've got some kind of oscillation. We've got some kind of oscillation, but the oscillation is going to be decreasing because e to the at is going to be scrunching it down towards 0, because a is going to end up being some kind of negative value. So it's going to look something like this. Along that line, it's going to just kind of oscillate until it gets down to 0. Maybe it only does it once. Maybe it does it many times. It kind of all depends upon the kind of damping that we've got involved. So to kind of review here, if we have two distinct real roots to our auxiliary polynomial, we're going to have an overdamped system. If we have repeated roots, it's critically damped. And if those roots are actually complex, then what we have is an underdamped situation, and we're going to get that oscillation over time. Let's go in and let's take a look at some examples and work through some of these ideas. Let's suppose that we have a circuit and it has a resistance of 30 ohms, an inductance of 5 hertz, and a capacitance of 1/75 farads, and no EMF. And then we suppose that Q of 0 is going to end up equaling 5 coulombs, and that Q prime of 0 is going to end up equaling 3 amperes. So what we have here is we have a complete initial value problem. We have R equal to 30. We have L equal to 5. We have C equal to 1/75. We have Q of 0, or Q naught, equal to 5. And Q prime of 0, which is our I, equal to 3. So we'll set up our differential equation, and that gives me Q double prime plus 30/5Q plus Q prime, plus 1/1/75 times 5Q equals 0, because we have no EMF. A little bit of algebra gives us that Q double prime plus 6Q prime plus 15Q will then equal 0. Now, a couple things that we can do, if we want to figure out our damping without actually going through and solving this differential equation yet, we can. And so what we're going to get, we've got, remember that R squared minus 4L over C is going to end up being our discriminant there. And so that's going to end up being 30 squared minus 4 times 5 divided by 1/75. And that ends up equaling negative 1200. So that's negative. What that tells me, because it's negative, it tells me that this system is underdamped. So we've got an underdamped system. Now, what I can do is if I want to go in and I want to solve this system, I can also see that it's underdamped just by looking at the solution. So I go in and I do that. I construct my polynomial, R squared plus 6R plus 15, set it equal to 0. And so I get R equals negative 6 plus or minus the square root of 36 minus 4 times 15 divided by 2. And when I solve that, what I end up getting is end up getting negative 6 plus or minus the square root of 24 all divided by 2. And that ends up giving me negative 3 plus or minus the square root of 6. Now what I can do is I could turn that into my solution. So that's my R. And so that means my solution, y of t, is going to end up equaling C1. Rather, I'll take e to the at. So my a is going to be the negative 3. So e to the negative 3t times C1 cosine root 6t plus C2 sine root 6t. And that's in my standard form. Now, what if I want to change it to phase mode? Well, to change to phase mode, what I'm going to need to do is I'm going to first need to solve for C1 and C2. So let's go in and do that. So if we put this into phase mode, like I said, we're going to need C1 and C2. So C1 ends up equaling 5, and we end up getting C2 equals 3 root 6. And basically, we're just going to use our initial conditions in order to find those. And so consequently, what we're going to get is that A naught is going to end up equaling the square root of 5 squared plus 3 root 6 squared. And so that's the square root of 25 plus 54, which equals the square root of 79. Our phi is going to end up equaling tangent inverse of 3 root 6 divided by 5. And so that ends up equaling 7,593 divided by 7,801. So there's your phase shift. So when we rewrite this in phase mode, what we get is we get that y of t ends up equaling e to the negative 3t times root 79 cosine root 6t minus 7,593 divided by 7,801. Now, by the way, a couple things here. Because that we have the complex roots here, R is complex, that tells me that we have an underdamped system. In addition to that, because we have a solution of this form where we have those trigonometric values inside of our solution, that also tells me that my system is also underdamped. Let's take a look at the second example. Let's suppose that we have a circuit with no resistance, inductance of 1/2 henries, and a capacitance of 1/2 farads. An EMF with an equation of E of t equal to 4 cosine 2t volts supplies a continuous charge to the circuit. And then we suppose that Q of 0 equals 8 coulombs and Q prime of 0 is going to equal 12 amperes. So now we have R is going to end up equaling 0, L equals 1/2, C equals 1/2, and we have that E of t now, my EMF, is going to equal 4 cosine 2t. We also have Q of 0 equal to 8 and Q prime of 0 equal to 12. So what we're going to do now is we're going to plug that into our differential equation. We're going to get Q double prime plus 0 over 1/2 Q prime plus 1 over 1/2 times 1/2 Q equals 1 over 1/2 4 cosine 2t. So this is then Q double prime plus, this zeroes out so that we have no resistance or no resistance term there, plus 4Q equals 8 cosine 2t. In order to determine our damping and also to find the complementary part of this equation, what we're going to do is we're going to solve the homogeneous part. So we're going to have Q double prime plus 4Q equal to 0. We need to solve that. So our polynomial is going to be R squared plus 4 equals 0. And that means that we get R equals plus or minus 2I. In addition, if we were to go in and solve for the discriminant in that term that we had before, R squared minus 4L over C, what you're going to see, because R is 0, we get negative 4 times 1/2 divided by 1/2, and that ends up equaling negative 4. That's what we end up having underneath that term. And so consequently, we can see here that this system is in fact underdamped. In fact, with no resistance, you can imagine that we're going to get a lot more oscillation of that charge. That charge is going to diminish less quickly than if we had some kind of resistance on the circuit. Now, given the fact that I have a solution of R equals plus or minus 2I, that actually tells me that Q of t equals, and we're going to get no e to the a term. We're just going to have the b term here. So it's going to end up being C1 cosine 2t plus C2 sine 2t. Now that we've solved the associated homogeneous part, what we need to do now is we need to find the particular solution that will allow us to solve the non-homogeneous differential equation. So we're going to need a trial solution. In our trial solution here, we're going to have QP of t as our trial solution. It's going to start out with, because of this 8 cosine 2t, it's going to start out as a cosine 2t plus b sine 2t. But since we actually have cosine 2t and sine 2t as our homogeneous solution, we're going to have to actually modify. So we're going to modify by multiplying the whole thing by a t. Then what we'll do is we'll take the second derivative and we'll plug that in along with the original function into the original differential equation, and then we're going to solve for a and b. When we do that, we're going to end up getting a equals 0 and b equals 2. So QP is going to end up equaling 2 sine 2t, and then we need to multiply that by a t, so it will actually be 2t sine 2t. So our differential equation is going to end up being q of t equals c1 cosine 2t plus c2 sine 2t plus 2t sine 2t. Now what we'll need to do is we'll need to go figure out what c1 and c2 are. When we do that, we end up with c1 ends up equaling 8 and c2 ends up equaling 6. So consequently, we get q of t is equal to 8 cosine 2t plus 6 sine 2t plus 2t sine 2t. And that is the model for our differential equation in standard form. If we want to change that to phase mode form, what we'll do is we'll figure out first what a naught is. And remember, a naught is going to end up equaling c1 squared plus c2 squared. So it'll be 8 squared plus 6 squared, which ends up equaling the square root of 100, which ends up equaling 10. And then our phi is going to end up equaling tangent inverse of, in this case, c2 6 over 8, which is approximately 0.6435. So what we do now is we're now going to put that into phase mode form. So our new q of t is going to end up equaling a naught, and it's just going to be these two parts. A naught, which is 10 cosine 2t minus 0.6435. So putting in our phase shift plus 2t sine 2t. And that is the phase mode form for our underdamped circuit system. The final concept that we want to deal with here is we want to deal with this idea of a steady state solution and a transient solution. And basically what the steady state solution is the limit as t approaches infinity of our differential equation q of t. And for the most part, that's going to end up giving me qp of t. And we'll take a look at kind of why that's going to be the case in just a second. It has to do with how it is that we set up the solutions to these particular systems. The transient solution, right, which is the one that kind of goes away, hence the word transient, is going to be qc of t, and it disappears or it becomes negligent as t gets really large. So let's say, for example, I have q of t, and let's say q of t is e to the negative 3t times cosine, and we'll put it in phase mode form. Let's have it be 2 cosine square root of 6t minus pi over 2 plus, and let's have this be 6 well, let's have it be 6 cosine 4t. Now, if we take the limit as t approaches infinity of q of t, what we end up getting is this part here, this goes to 0. This ends up equaling 0 plus, and then we get really 6 cosine 4t because we're just going to get oscillations. Whatever that value is in terms of the oscillations, it's just going to be that 6 cosine 4t. Because the e to the negative 3t is going to overwhelm the cosine part here inside of our homogeneous part, okay? And if you look at the structures of these circuits, this would end up being your QC, and this ends up being your QP. Because the nature of these systems, especially if we have resistance, is that in the absence of any kind of EMF, we're going to get the charge going down to 0. And if we put it in EMF, then we'll basically get whatever part is a result of that electromagnetic force putting charge into the system. And so consequently, that's how we can differentiate between what's our steady state and what's our transient. Steady state is going to end up being QP, the particular solution that we get because we've got an EMF, and our transient solution is going to be the part that has to do with that associated homogeneous differential equation. So that finishes up finding the solutions to circuits, and I hope you enjoyed it. I hope you also noticed that it's really a lot like working with spring mass systems. If you've done any work with spring mass systems, the mathematics is virtually identical, and the terminology is pretty much the same. So if you kind of get one, you get the other. It's just like how they get interpreted from a physics perspective is different. If you need some work working with undetermined coefficients or solving differential equations that have constant coefficients, I'll put those links inside of the show notes. If you liked the video, go ahead and press like. If you have any comments or questions, go ahead and comment and question. And if you like the work that I'm doing and you want to see more of it, or you're just curious about more differential equations, linear algebra, discrete mathematics, any kind of mathematics really, go ahead and subscribe to the show.